Good evening and welcome to the live session. It is 6 p.m., but participants are yet to join. So we'll wait for a few more minutes before we start. Thank you.
That I'll explain you. But as you can see, the rotating spray further, the deposition rate keeps on increasing.
Good evening and welcome to the live session for the NPTEL course on the fundamentals of additive manufacturing technologies. This course is taught by Professor Sajid Kapil, who is a member in the faculty of the Department of Mechanical Engineering at IIT Guwahati. I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. This is the eighth week of the live session, so we are past the halfway mark, and this has been a really transformative and a learning experience for all of us, I would say. In the past week, the contents of the course mostly were related to wire-based additive manufacturing processes and specifically metal inert gas worm and tungsten or plasma inert gas worm. So we'll just quickly revisit the concepts and the principles that were discussed in the lectures. And then we'll solve a few example questions which might be useful for your assignments and even for the certification exams should you have registered for it. Now, just like the subsystem based classification of all the AM processes that we have been studying, similarly for the case of these metal wire additive manufacturing processes, the material, um, as the title suggests, would be only metal, and the flow in this case is also predominantly of continuous type. I am not really aware of any drop on demand metal systems. However, I have followed some new technologies which have come up, which have the say the title of molten metal deposition or similar, which might be a drop on demand technology, but I'll have to check that and I'll get back to you if that turns out to be the case. The machine kinematics in this case may either be purely serial, purely parallel, or a combination of the two. Typically, we encounter serial kinematics in most of the say established or existing machines, but parallel and hybrid kinematics are also coming up. The energy source that we're focusing on, that was focused on in this past week, was mostly arc. We'll also be looking at energy beam processes in the subsequent week, typically electron beam and laser beam type processes. And as we had been discussing, the support mechanisms in this case typically are not encouraged because it will be very difficult to get rid of them. Instead, what we do is we either stick to very simple geometries that do not really require supports, or on the other hand, we use multi-axis kinematics, which is actually a more practical solution. The other one is pretty restrictive. For the case of uh, some processes like we looked at in last week, an acid bath could have been suitable when copper was used as a support structure for making parts out of stainless steels. However, that was a very say limited or isolated example. Typically, we would like to either avoid support structures altogether or we resort to multi-axis kinematics for building parts that are of a more complicated geometry, have overhangs, and thus in the normal uh, sequence of things would have required supports. Now, just a brief throwback to the MIG-based welding or warm process. Both of them are quite similar, in fact. So, in this case, a metal inert gas welding gun is used to add the material on a substrate. Uh, you would find that typically this welding gun is retrofitted on an existing 3-axis or 5-axis CNC machine and functions almost as well as a new AM machine. And this MIG welding, typically referred to as gas metal arc welding, utilizes a consumable electrode and hence yes. Other processes such as flux core arc welding may also be counted under the term MIG, and the typical setup is shown here. So you have this wire feeder which feeds the build material into the MIG torch, and this wire also acts as one of the electrodes. So based on the type of process that you are using, whether it is DC electrode positive or DC electrode negative, it can have either polarity. In the case of AC, of course, its polarity keeps on switching. Then you have this nozzle through which this wire is fed out, An arc is established between this wire and the pre-deposited layer or the substrate plate. An arc, as we know, is just so typically when electricity is flowing through a wire, the air or the coating around it is typically insulated, and this insulation, what it does is it restricts or it constricts the path of the electric flow to the wire itself. However, in certain cases, such as say when the amount of energy that is being transmitted is really high, or for some other reason the air surrounding the wire becomes conductive, then rather than going through the wire itself, the electricity can also flow through the air because of ionization. So the air becomes ionized, the electrons become start moving freely, and this rapid and almost free movement of electrons provides an easier or more, say, less energetic path, that is a path requiring less energy for the current to flow. Thus, the current can in fact flow through the surrounding air, and that is what is called an arc. This arc may produce temperatures up to some 6,500 degrees Celsius, which is sufficient for melting most metallic or in some cases also some types of refractory materials. This arc and the heating generated by it is used in the case of say this arc-based welding processes, and in this case also arc-based AM processes. Again, this arc is shrouded on all sides by this inert gas. So the inert gas ensures that there is a the oxygen and surrounding atmosphere is displaced from the region of the molten weld bead, and only a pure deposition of the intended build material is done through the bead. Now, the consumable electrode, as we said, is in the form of a wire reel. Typically, it will be your welding wire, typically of say 1.2 or 1 mm diameter. It is fed at a constant rate through the feed rollers, typically, but then this rate can, as we know, it can be controlled by us. And in the case of MIG-based processes, this rate of the feeding of the wire is also closely correlated to the current which forms in the circuit. We'll also be looking at it further. Now, the welding torch is connected to the gas supply cylinder, which provides the necessary inert gas for shrouding. Electrode and workpiece are connected to the power supply, as we discussed. Based on the type of application we are targeting or on the type of material we are going to work with, we can assign negative or positive polarity to the workpiece. Or in the case of AC, it will be constantly switching. The power supplies typically are of the constant voltage type only, and the current from the welding machine is changed by the rate of feeding of the electrode wire. So the current is closely correlated to the rate of feeding of the wire. Now, based on whether you are working with a DC power supply or an AC power supply, the deposition characteristics change. DC arcs are typically preferred because you can control the amount of heat input. And in the case where the work is given positive polarity, about 70% of the heat is liberated near the anode or the work. And thus, if more heat is required at the workpiece side, say you want a deeper deposition or you want more dilution, or maybe to enhance the bonding strength, you want that the amount of dilution should be significant. The workpiece can be made as anode, and this leads to 70% energy being liberated near the workpiece. This configuration typically referred to as direct current, which refers to the electricity supply type, and your electrode being negative gives rise to a higher penetration, as shown in figure A. If we were to reverse the polarity, that is the work is now negative, or your electrode is positive, direct current electrode positive or DCEP. In such a case, more heat is liberated or more energy is liberated at the electrode rather than at the workpiece, and thus your beads tend to be shallower. However, the amount of deposition in this case will be higher. So, say you want to deposit higher volumes per unit time, and maybe the strength is not your greatest concern, just sufficient strength of the part is enough. In such case, you may opt for such a polarity which is DCEP. In reverse polarity, of course, the penetration is small. And in the case of AC welding, the bead obtained has characteristics which are intermediate between these two extremes. And as Professor Kapil pointed out, such AC welding source may typically be preferred for the case of aluminum or aluminum alloys, because as we know, these tend to get oxidized very easily, and the oxide layer which forms on the surface of aluminum is much harder and has a far higher melting point than aluminum metal. Thus, we would like to get rid of this aluminum oxide layer, and to do that, we will resort to an AC type of welding source, because what will happen is, say you have this electrode here, and they are both connected to an AC source. So in the cycle that your workpiece is negative, the electrons will flow from the workpiece towards the electrode or the wire. Thus, electrons will be liberated from the aluminum and they will hit the aluminum oxide layer and will tend to break it. Thus, when the polarity reverses and now your electron, the wire electrode is positive, negative, then electrons will come from the electrode onto your base metal and will be able to deposit much more easily than in the case where an protective layer of oxide would have formed. So, AC welding source is typically preferred for deposition or welding of aluminum. Here we also have the various types of metal transfer methods and the deposition rates. And this list is ordered from a lower to a higher deposition rate. The various metal transfer methods are short circuit or dip transfer, globular transfer in which the molten metal takes the form of small globules, small discrete globules, which transfer a certain quanta or volume of material at a time. Then you have spray transfer, where fine droplets are transferred in the form of a spray-like pattern. Then you have pulsed spray transfer and rotating spray transfer. Typically, we find that for rotating spray, the deposition rate in kg per hour can be as high as 6.3 to 13.5. And as some of us would already be aware, specifically those of us working in AM or AM like processes, perhaps wire and arc additive manufacturing is one of the few processes which has really high deposition rates and which can actually be deployed for actual commercial usage. However, because of this higher deposition rate, we also tend to lose out on the geometrical accuracy, and thus the parts which are produced do not really tend to be, say, very near net shape. However, with post processing, uh, a certain extent of post processing is anyway required for most AM processes. So here also post processing can be used to achieve the desired shapes. However, for simple geometries and large builds, WOM is the process of choice. Again, these metal transfer methods are also, and the deposition rates associated with them will vary as per the varying rates of current. And the lowest rate of current will give the is observed in the case of the short circuit transfer. And as with the deposition rate, the current is also in increasing order. Now, in short circuit metal transfer, what happens is the wire initially is at a standoff distance from the base metal or the pre-deposited layer. Then it is as it is fed, it comes in contact with the build plate. The circuit is completed and short circuit happens. And because of this short circuit, the current that flows through the circuit increases tremendously, also leading to high amounts of heat being generated, because as we know, the amount of energy is equal to I square RT. So it is proportional to square of the current. Because of this large increase in current, the wire melts immediately and the short circuit is broken. And then this process repeats for deposition of metal. In globular metal transfer, the molten volume of metal takes the shape of small globules or small, almost sphere-like geometries. And once the droplet becomes heavy enough, it detaches from the wire and falls onto the pre-deposited layer of the substrate and forms the bead. In the case of spray metal transfer, as we discussed, the metal is dispersed in the form of small droplets, which are constantly sprayed on the deposited layer. In pulse metal transfer, you have, rather than having constant current characteristics, you have something similar to, say, a square waveform here. It can also be rectangular. And you have these two. So this bottom level or the lower level is what is your background current. The background current is useful for maintaining the arc and ensuring that the arc is not getting extinguished. Whereas this higher level of current, called the peak current, is actually your welding current. And as you would have seen in the video, during pulse metal transfer, it appears as if the entire setup is pulsing, that is, the brightness keeps on fluctuating. At lowest brightness, the process is corresponding to the background current, that is, only the arc is being maintained. Whereas at highest intensity or highest brightness, it is corresponding to the peak current, at which the metal is getting molten and separated from the metallic wire and getting deposited. For calculation of power, we will say resort to some intermediate or mean current, and thus the it may be seen that this process is also more efficient in terms of power consumption, and it is also stated that this is the most suitable method for warm. The other are the rotating spray metal transfer types, where the spray, in addition to falling vertically, is also given a spiral-like motion so that it is distributed in a larger footprint on the XY plane. Thus, the amount of deposition that you get will be shallower, but then the bead width will be higher. One of the prevalent technologies in this day and age is called cold metal transfer. Contrary to the name, it's not that this is occurring at some cryogenic temperature. It's just that the temperatures which are achieved in this process are lower compared to some of the other conventional processes. It is one of the most preferable MIG welding processes due to low heat input characteristics, and it utilizes an alternating thermal arc pool. The melt pool is hot when the arc is initiated. However, it is cold when the arc is extinguished and the wire is retracted. So previously, for the case of this short circuit based metal transfer, we were relying on the metal wire coming in contact with the pre-deposited layer or the substrate. Because of this, a short circuit would have occurred, which would have raised the amount of current in the circuit, and this increase in current would have led to melting of the material, and then the short circuit would have been broken and the process would continue. However, this case is slightly different. So initially it is similar, the arc is initiated and the filler metal moves towards the weld pool. As the current is less, the filler wire dips into the melt pool and the arc is extinguished. Now previously at this stage we would have raised the current, or the current would have raised in the circuit, leading to melting of the wire and then re-establishment of the arc. However, in this case, rather than resorting to that, the wire itself is retracted, and this assists the detachment of droplet during the short circuit instead of utilizing a current impulse, as in the case of short circuits based metal transfer. Now, once the desired gap is obtained, the wire is moved back again into the weld pool, and this process continues. This video is also showing the same. So here at this stage, the arc has been established and the wire electrode is away. Now with time, this wire will progressively move towards the molten pool. Once it comes in contact, this molten metal that you see here, it will also continue to grow with time because of the effect of the arc. At this stage, when short circuit occurs, we will begin retracting the wire. And what happens is the molten metal remains attached to the bead, whereas the solid wire electrode detaches. When it is fully detached, the arc is established again because the short circuit is broken, and this process continues. Now, similar to most other AM processes, MIG-based BOM also has a typical process cycle, starting with a CAD model as per the definition of AM, and you have the typical pre-processing, building, and post-processing steps, which lead you to the final component. Interestingly, during this uh, building process, some further in situ processes may be incorporated, such as in situ rolling, that is, you deposit one layer, and then before depositing the next layer, you immediately roll it. This will allow you to, say, change the microstructure in this deposited layer. It may also help in maintaining the Z height accuracy or the surface flatness, and it will change the mechanical and metallurgical characteristics of the final build part. You can have some in situ short pinning arrangement, which will introduce compressive residual stresses into the surface, or may also help in alleviating tensile residual stresses, should the case be. We may also resort to an in situ hammering step, where after deposition of each layer, the entire layer is hammered with, say, a pneumatic hammer, and this also has effects on the final metallurgical and mechanical properties of the deposited part. We could also have some interpass cooling, that is, say, either by increasing the time between deposition of two layers or by deploying some additional enhanced cooling mechanisms for cooling of each layer before the next layer is deposited. And as you know, because of this change in the thermal characteristic during deposition, it is expected that the microstructure, say the segregation profiles and other properties will be affected. Additionally, we can have a face milling step, which typically you would do to maintain the Z height accuracy. In IIT Bombay, Professor Karunakaran and his team have developed a novel AM machine which incorporates many of these in situ processes, and it is referred to as hybrid layered manufacturing, or HLM, because in each layer you're performing these in situ processes to improve the overall functionality and properties of the part. Finally, once you have your built material, you would resort for some typical post-processing steps such as a finish milling cycle or a heat treatment if the case should be, and then you end up with your final component. Again, as we were discussing in our previous session, whenever we are trying to establish an additive process for, say, any new technology, or more typically for any new material, we have to go through a few number of basic experiments. The most fundamental of these being the single bead experiment, where on a substrate you deposit only one single bead of material, say along the x direction, and you vary the process parameters. So you may vary the power or the scan speed or the wire feed rate. In some cases, you may also vary the standoff distance between the nozzle and the substrate, and you try to optimize the bead characteristics. Typically, what we'll be looking for is, say, the dilution. So if this is my substrate and this is my deposited bead, we would like to know how much of the bead actually penetrated into the substrate, and we would like to check the height and width of the bead and correlate it with our input, say the wire dia or the designed thickness that was expected. Would also like to see what is this angle that the bead is forming with the substrate and whether the bead profile is concave or convex. Once your single bead profile or your single bead process parameters are optimized, we opt for a multi-bead build experiment, in which case the additional consideration of step over or a hatch distance comes into the picture. So after one deposition of one bead, at what distance from this center do you deposit the next bead? And that will, of course, decide the overlap. And based on varying the step over or the hatching distance, you will end up with different characteristics. So, say in some cases, you may end up with a surface which is almost flat, whereas in some other case, you might end up having these large undulation. Once your single bead and multi-bead characteristics are optimized, then you opt for the multi-layer experiment. In some cases, rather than having multi-beads in the XY plane, we may also have multiple beads along the Z direction. And it is only after this that we opt for the multi-layer experiment and then end up printing our final component. The process parameters which play a key role in each of these experiment types are the power in terms of the arc voltage and the currents being the starting, main, reduced and final currents, the filler material, so the wire type, whether it is coated, uncoated, cored or not, the diameter of the wire and the wire feed rate, the shrouding gas that you use, its purity, proportional, its pressure, and for what duration of time did you have the gas flow before the start of print and after the after the print. The deposition parameters itself in terms of the layer thickness, the bead width, the bead height, the distance of the torch, distance between node and bed plate, also called the standoff distance, the distance between electrode contact tip and base plate, because as we will see in the case of TIG or plasma welding, it's not always the case that the electrode is, say, revealed outside, and in some cases it may also be concealed inside the hollow nozzle, and it may be the plasma which is actually interacting with the substrate, and the speed at which the torch is moving. And in terms of path, the type of area filling or the area filling strategy about which we have studied, so whether it is a zigzag, bilinear, or say a spiral or any other contour based technique, and the step over increment. Some simple or basic geometric modeling of the bead characteristics was also discussed. And here you typically assume that the build profile above the substrate or the for the deposition is in the form of a mathematical parabola, and we express this parabola in terms of the known parameters or the measurable parameters, which are the height of the bead and the width of the bead. This gives us the geometric form of the parabola as y equals h times 1 minus 2x by w square, h in this case being the height of the deposition above the substrate and w being the width of the deposition as measured on the substrate surface. So on this surface. Now we would also like to express the same mathematical expression in terms of the process parameters VW and VT, because it is the process parameters that we control. The measurable properties such as the height and width of the bead are our say desirable outputs, but we do not explicitly control them. What we control are the process parameters such as VW and VT, the velocity or the feed rate of the wire, and the traverse speed of the torch. This is achieved by equating the expressions of bead area obtained in terms of geometric and process parameters. So for a parabola, we know the area which is enclosed by it is equal to 2/3 h times w. And if we express it in terms of the process parameters, this will come out to be pi d square by 4 times Vw by Vt. And upon equating, we obtain W is equal to 3 pi Vw d square by 8h Vt. Upon replacing this into our equation for the parabola, we have y equals h times 1 minus 16h Vtx by 3 pi Vw dw square whole square. So now your bead profile is expressed in terms of one geometric parameter h and two process parameters Vt and Vw. However, this is a very simplified model relying only on the geometric characteristics, whereas in reality, the bead formation is the interplay of several complex physical phenomena involving gravity, electromagnetic or Lorentz forces, viscosity, surface tension. In some cases, it may also include effects of, say, the presence of any surface active elements such as sulfur, as we have seen that in low amounts or for low ppm of sulfur, the weld bead which forms is, say, fairly uh, typical, whereas if the presence of such surface active elements such as sulfur is increased to say 150 parts per million, suddenly your bead becomes very deep. And this is because it reverses the sign of the surface tension gradient, thereby modifying the Marangoni forces or affecting the direction of the Marangoni flow. Therefore, although both H and W depend only on the process parameters, obtaining their relationship in terms of the process parameters alone is too difficult as it would involve modeling of all of these phenomena that were discussed. This given equation thus is simply a hybrid form of the parabola that includes some easily measurable geometric properties, being the height and width, of which the height is more useful. Once h is measured and the prevailing process parameters are known, the bead profile can be obtained from this equation. Now, as we also spoke about, for the case of MIG-based welding, the current which flows through the circuit is closely correlated to the wire feed rate. And in some cases, the wire feed rate may not be the most easily measurable uh, parameter. In such a case, we can rely on this working curve to find the wire speed given the current, and then we can proceed with our design considerations. It is also known that for most welding machines, this trend is linear. Now, this is another case study for the geometric modeling of multi-bead in the XY plane. And here, the objective is to actually achieve a flat surface, such as shown by the line, say HLJ here. That is, after deposition of two beads, you want the composite bead to have an almost flat surface because this is the most ideal or most desirable outcome. And it is proposed that such an outcome will be achieved only in the case when the overlapping volume is equal to the volume of the valley, or this overlapping volume, which is common to both of the beads that I have highlighted in red, is equal to the volume that is encapsulated in this valley between the two beads, which I have highlighted in green. Whereas for other cases of inequality, such as in the case when this overlapping volume is less, then you have this drooping type of surface which forms, or if this overlapping volume is very high, then the surface bulges out. And this is achieved by certain geometric similarities and equality. And the final outcome suggests that the optimal step over, as shown by P here, which is nothing but the center to center distance between two adjacent beads, should be equal to two-thirds the bead width. So if the width of one such bead as shown here is W, it is assumed that both of these beads, if deposited independently, would have the same characteristics, and the two are just superimposed. So we want to deposit the next bead at a distance which is two-thirds the width of this single bead. However, I'm not sure whether this result has been validated against experimental trials or not. We may look up this reference, and that might tell us more about it. And a numerical example in this context has also been solved. So let us just quickly visit this. So in a MIG welding based wire arc additive manufacturing process, the following process parameters are considered. Torch speed is 800 millimeters per minute. Uh, this is on the higher side if you ask me. The bead height is 2 mm. The penetration depth being 0.5 mm. Wire dia is your typical welding wire 0.8 mm. The welding current is 100 amps. The material density is 7.8 gram per cc. Efficiency of the process is 90%. And for this, process, we are supposed to calculate the deposition rate in grams per minute, the bead width, the optimal value of the step over, and the approximate value of the required power, with certain assumptions. The first being that the bead cross section is parabolic. The given working curve gives us the relationship between wire speed and the current, and some material properties such as Cp, melting temperature, room or ambient temperature, and latent heat of fusion are given to us. First of all, the wire speed, as we discussed, can be calculated from this working curve. It is given that the arc current is 100 amps. So, as highlighted in the red line here, we draw a vertical line at 100 ampere current. It intersects the curve at this point, and that intersection, which when connected to the y-axis, is gives us a value of approximately 8.4 meter per minute. Once this is done, we can calculate the deposition rate, which will be AW, or the area of the cross section, times the wire speed times density. This gives us the volume, which is deposited per unit time, times the density will give us the mass per unit time. So it is in gram per minute. Now the area of the cross section is simply pi by 4 d square, where wire dia is 0.8. So this is the amount of material which is flowing out. Comes out to be 0.16 into 10 power minus 6 times pi meter square. Rho is given to us. Thus, we know the amount of deposition rate in gram per minute, which comes out to be around 33 grams per minute. Now we need to find the bead width, and we already have the expression for it. W is equal to 3 pi VW d square W by 8h Vt. Vt, or the torque speed, is given to us. Diameter of the wire dW is given to us. VW we already found from the working curve. So this W can be calculated, and this comes out to be approximately 4 mm. More exactly, it is 3.96 mm. Once W is known, as we saw from the geometric modeling, the optimal step over is simply two-third this width, all other assumptions remaining the same. So similar calculation is performed here. Two-third of the width comes out to be 2.64 mm. Now, once all of these geometric parameters are known, we are required to find the energy required for this, or the minimum energy required for this process. And so, if we look into it, this process actually involves two transactions of energy. The first transaction being melting of the wire, which leads to deposition of this bead. The second transaction is the melting of substrate. So the final power calculation is also divided into say these two phenomena. First, we account for the energy required for melting the wire. So typically, it will be your the amount of energy per unit volume would typically be rho Cp delta T. Sorry, that would be per unit mass. The amount of energy required per unit mass would be rho Cp delta T, because Cp is typically expressed in volumetric terms. All of these terms are usually, say, in terms of per unit volume. Here, however, L is given in terms of joule per kg. So you have rho Cp delta T plus L, and then you multiply it with the unit volume that is flowing out in 1 unit time, which is AW into VW. Similar for the case of the substrate, divided by the overall process efficiency to come up with the minimum power required. For a more in-depth detail of all the calculations, you may refer to the video again, because Professor Kapil has broken down each of these steps. However, till now we were discussing about multi-bead deposition in the plane or in the XY plane. And in that case, the substrate which the deposited bead encountered was always horizontal, apart from this small region, of course, where this bead would have overlapped with the existing bead. But for most of the case, or for most of its deposition area, it would have encountered a flat substrate. However, when we are trying to deposit these thin-walled structures, such as these ones shown here, here you have a right circular cylinder, a hollow cylinder. Here we have a hollow cube with four walls, and this is, say, like a hollow triangular section. These thin walls are often just one or two walls thick. So you just keep on depositing single beads one over the other to form these thin wall structures. And in such a case, the substrate is curved because of the presence of the previous bead. It is expected that the parameters that we have optimized for the flat substrate need not carry over and definitely do not carry over to this deposition cycle when the substrate is flat, and also the distance between your nozzle and your substrate will change. The standoff distance will change. In the case of, say, energy beam type processes, this will also lead to defocusing of the beam, and that will lead to change in the input energy density, and finally the overall build characteristics. So when we deposit the first bead on the substrate, its base is flat. However, the base for subsequent deposition of the beads no longer remains flat. The height and width of the bead deposit on the curved base has to be calculated so that the arc gap can be maintained uniformly throughout the process, because we know upon changing this arc gap, the metallurgical and mechanical characteristics of the process will of the part will change, and this may lead to undesirable anisotropy. In the previous case, the bead profile was assumed to be parabolic. However, in this case, it is assumed to be the arc of a circle, just for simplifying the calculations. So here it is assumed to be an arc of a circle. The center is assumed to lie somewhere inside the substrate, of course, depending on your actual case. And this circle can be displaced in the plane of the slide to say best match with your observed bead. It has a radius r, and currently the chord of the circle which coincides with the substrate is subtending an angle of 2 theta 1 at the center, so half of it is theta 1. In such a configuration, the width W1 is simply equal to 2r sine theta 1, because if we consider this right angle triangle, okay, this is too thick. If you consider this right angle triangle, then this hypotenuse is r, the angle enclosed is theta 1, so this height becomes r cos theta 1, and the perpendicular becomes r sine theta 1. This is what is shown here as well. So W1 is twice this length, so 2r sine theta 1. The height d is r cos theta 1. And there's h1, which is simply the radius r minus. So this distance, as we know, is the radius r. And then you have d, so r minus d, or r minus r cos theta 1, so r times 1 minus cos theta 1. Now we want to find the area A1 of the deposited bead. We are looking only in the plane because we assume that, along the uh, along the print direction, which in this case would be the x direction, or into the plane, we assume that this bead profile remains uniform, and Thus, the variation is only occurring along this plane or the two dimensions. So to find the area capital A1, we divide this composite geometry into simpler geometries consisting of this sector with an area of, sorry, this sector with an area of small a1 and this triangular region with an area of small a2. A1 again is very easily calculated given the angle subtended by the arc. So this is simply r square theta 1. We are already familiar with this formula. If had half of this angle been equal to pi, which would have corroborated to this complete circle, the area would simply have become r square pi or pi r square. For this triangular region A2, the area simply comes out to be, because it is a right triangle, so half into base into height. So half into r cos theta 1 into r sin theta 1 or half r square sin theta 1 cos theta 1. Once these two areas are known to us, we find the area of the highlighted region A1. A1 is simply A1 minus small a1 minus twice small a2 because this area is also has an area equal to a2. This comes out to be simply r square times theta 1 minus sin theta 1 cos theta 1. Now these calculations are revisited again for some further simplification. So we already found W1 is 2r sin theta 1 and H1 is r into 1 minus cos theta 1. Thus, if we divide these two to eliminate r, we obtain an expression for theta 1 only in terms of the measurable parameters H1 and W1. The steps are shown here. So first we square, and once you have this cos square theta term and sin square theta term, you want to add them up. So you add 1 to both sides as shown here. Then this leads to further simplifications. Now 1 plus cos square theta 1 plus sin square theta 1 becomes 2. We have 2 minus 2 cos theta 1 by sin square theta 1, yeah, as shown here. And then 2 by sin theta 1 is taken out common, and 1 minus cos theta 1 by sin theta 1 remains. But this is similar to this expression right here. So we rewrite it, and finally we end up with an expression sin theta 1 equals 4h1 w1 by 4h1 square plus w1 square, which gives us an expression for theta 1 in terms of the measurable parameters, which is equal to sin inverse 4h1 w1 by 4h1 square plus w1 square. This is reproduced here. However, this was the first bead which was deposited on a flat substrate. We want to calculate the area or the height of any intermediate bead which would have been deposited after some n number of beads. And typically why we want to perform this exercise is, say, when I deposited this single bead, the height h1 which I was getting was equal to, say, 1 mm. I want to build a part with a total height of 10 mm. So do I just need to deposit 10 such beads? Because when you make it into a CAD geometry, this is what you will see. Because typically, say we will just slice it into uniform layers. We know that the thickness of each single, the height of each single bead is 1 mm. So it is, I mean, almost obvious to assume that after depositing 10 layers, you will end up with a final height of 10 mm, and that will be adequate for whatever part you desire to build. But upon cross-checking with such an exercise, we find that the actual height in most cases would actually be the less than the design height. And thus your build geometry will be totally compromised. So we should account for it and must compensate for this at the design stage itself. Now, when we are investigating the height of any intermediate bead, such as the one shown here, and this height is denoted by Hn, we first start by finding the area of the cross section of this n plus 1th layer. And this is again a composite geometry. We can get this area AN by having the area EKFO n plus 1. So this is EKF and O n plus 1. So something like this. We add the area EON. So EON F ON plus 1. So this almost rhombus like shape here. Then we subtract ELFON. So ELF and ON. And this composite operation will actually give us the area AN, which is highlighted in black here. And it is easy to find expressions for all of these. This AN simply comes out to be r square pi minus theta n. The first simply based on the area, the angle subtended by the arc at the center, which is pi minus theta n. For this rhombus, we break it into these four triangles and find the area of one such triangle multiplied by 4. For each such triangle, it is simply half r square sine theta and cos theta n, as we saw previously, multiplied by 4. And again, for ELFON, it is just r square times the angle subtended by the arc at the center. In this case, it is theta n. So r square theta n. Again, another thing to note is that for this exercise, typically we'll keep the deposition parameters or the process parameters constant. So whether we are depositing this first bead here on the flat substrate, which takes an area 1, or this intermediate bead somewhere in the middle here, the amount of material which is getting extruded or deposited is still the same. It's just that it is redistributed differently in space. That is why the bead profile is different. However, the volume that was deposited still remains the same. So in a cross section, the area occupied by the bead should also be the same, given that we are scanning the same length. So this height, this area AN would in fact be equal to the area of the first bead A1. And we equate these two expressions. That gives us this nonlinear equation in terms of theta n and cos theta and sin theta n. Sin theta and cos theta n minus theta n equals half theta 1 minus sin theta 1 cos theta 1 minus pi. And Professor Kapil suggests that we can use commonly available numerical methods to solve such an equation. It might not be easy to solve it algebraically or by simple algebraic means, but it can definitely be solved numerically. Once we have the value of theta n from this equation, we can use that to find the height hn that is contributed by any such intermediate layer. So again, in another assumption, we assume that each of these beads will contribute a height hn. Is it a valid assumption? Uh, I cannot really comment, but I mean, it is reasonable to assume that the height of each such layer will be the same. However, practically, it might not be true because we know that the processes are not idealized, whereas all of these derivations are for highly idealized conditions and equilibrium conditions. So, nevertheless, we assume that each of these beads, subsequent beads, will contribute the height hn. The initial bead will contribute the height h1. Say after that you deposited some n minus 1 beads for a total of n beads, and this will be your final height of the deposited part. Now this h1 hn curiously is simply equal to this distance over here, or the distance between the two centers. So it is simply equal to half of this distance, as we remember, is r cos theta n. So Hn is simply twice r cos theta n. And once it is available, we can calculate the height of the final part. An example based on this has also been discussed. All of these expressions are already known to us. So a thin wall has to be built by a mid-based warm process. Single bead experiment first performed on a flat substrate. Assume a circular profile of the bead cross section. Find the height of the thin wall after deposition of 10 layers with the same process parameters. This is very important, else for each layer where the process parameter is changing, we would have to repeat this exercise and derive the expression. So for the first layer itself, we are seeing that the height is 2 mm, but the width is 4 mm. Clearly, the center is lying on the surface itself, and theta 1 is simply equal to pi by 2. This is also confirmed from the equation that we derived, so everything is consistent at this stage. Now for the nth layer, we have this expression for in terms of sine theta n, cos theta n, and theta n, where we input the value of this pi by 2, and that gives us the final expression theta n minus sine theta n cos theta n is equal to pi by 4. Professor Kapil used graphical means to solve for this. So this in green, you have the plot for theta n minus sine theta n cos theta n, and in black here, you have the plot for y equals pi by 4. This also is just y equals theta n minus sine theta n cos theta n. And as we know, the solution will lie at the intersection point. And here this point is almost close to 1.16. So once theta n is known to us, we find Hn, which is 2r cos theta n, which then comes out to be 1.597. Thus, the height after 10 layers, so n is equal to 10, is equal to height of the first layer plus n minus 1 times the height of each layer, assumed that all the layers are equal in height. This gives us the final height of the build, which is 16.376 mm. We saw that the height of the first layer itself was only 2 mm. So after 10 layers, one would naively assume that the height achieved is 20 mm, whereas in the actual case, it is only some 16.4 mm. The error is quite significant in this case. Now, another anisotropy, or another facet of anisotropy that we observe, is in terms of the mechanical properties, the most easily measurable of which is the hardness. So here is the trend of variation of hardness across the build layers, and we see these indents over here. So the researcher has taken a series of indents at what appears to be, say, uniform displacements or uniform distances along the build height, and then plotted those hardness values and found that in the initial few layers, say up to 10 layers or so, the hardness values are rather uniform, or they are distributed in a close spread. Whereas as the number of layers increases, especially in the final 4 or 6 layers, the hardness value has changed drastically. And neither are they closely spaced. They tend to spread over. They are spread around. Now, what can be the reason for this change in mechanical properties? Hardness is the only one we have measured, but it is expected that even other mechanical and metallurgical properties may have been affected. So when we look at it closely, the solid state thermal cycling may have been responsible. That is, once this layer has been deposited and the next layer comes on top of it, so if I just draw it, say the first layer was deposited, Now we are depositing the second layer. What happens is heat flow actually occurs by conduction through this previously built layer into the substrate, and it may also occur, it does occur by convection and radiation. Now, because of this conduction heat flow, and as we know that also because of the deposition of the next layer, some extent of dilution will occur in this previously deposited layer, and this small fraction of the volume will again be remelted and it will solidify again. This process continues as we continue building, and because of this additional exposure to heat and also this additional cycle of melting, the mechanical properties, the microstructure of the part changes, which in turn leads to the change in mechanical properties. This is called as thermal cycling or also solid state thermal cycling if melting does not occur. The hardness of the core is independent of the number of thermal cycles, and the variation exists only in the final layers. That is because these final layers are not really exposed to any thermal cycles. The thermal cycles are also plotted here, and we see that for the last layer to be deposited, no other layer is deposited on top of it. Thus, it is not really exposed to any form of thermal cycling. The layer before is deposited to one cycle of thermal cycling because of deposition of the next layer, two, and so on. So we see that for these bottom layers, say between layer number 1 to 10, the number of cycles are fairly high, 6, 8, or 12 thermal cycles. Thus, their properties are more or less consistent. Whereas for these upper layers, we have no thermal cycles or very few thermal cycles, which leads to this variation in the properties. Typically, these lower layers will have a coarse microstructure or larger grains, whereas this top one will have a fine microstructure. Of course, fine and coarse are relative terms. We are talking about the microstructure variation across this one build of a single material. This will vary as per the process and the material and the process parameters used. But if we are to see the variation along this one part only, towards the bottom, the microstructure will be rather coarse, whereas in the top layers, it will be rather fine. And as we know from basic material sciences, a finer microstructure often tends to have higher hardness compared to a coarser microstructure of the same material. Again, the anisotropy in these mechanical properties is also characterized in terms of strength, notably the tensile strength. And often we would like to check for the anisotropy properties along the build direction, the torque direction, and the step over direction. Also the z direction, so x, y, and z. And in one of the results, it was shown here that the z direction properties are weaker by about 20% in yield strength and 11% in ultimate strength, which is a significant number. And in this particular case, it was attributed to insufficient penetration or say lower dilution. Again, as we know, the current is closely correlated to the amount of penetration because it dictates the energy input to the material. And here, one study showed that with increasing current, the ultimate strength also increased because because of the increased current, the input energy density increased. Because of the increased energy input, the penetration of the bead increased and the diffusion or the bonding was stronger, which led to higher ultimate strength. Now we look at some of the defects, uh, typical defects of MIG-based warm process. One of them, one class of these defects is the residual stresses and distortion. So residual stress is remaining stress in part after removal of all external forces. They may lead to distortion of the part and thus a loss of geometric accuracy. It also adversely affects the fatigue life of the part. Now, if the residual stress in the part is more than the ultimate tensile strength itself, it will lead to fracture, as we know. This fracture will occur via cracking. If this residual stress is larger than the yield strength but lower than the ultimate tensile strength, it will lead to some uh, plastic deformation, that is, some warping will occur. It is These residual stresses are inevitable, and it is almost impossible to eliminate the residual stresses completely from the part produced by warm. However, we can mitigate it, and some of the common models which have been proposed to study the generation of residual stresses are the thermal gradient model and the cool down phase model. I am not really familiar with either of them because I don't work in residual stresses, but if someone is, I would be really happy to discuss. And the loading and loading cycle is also explained here. So typically, when the material is being deposited, and we see this Gaussian distribution of energy here as well. So when this part is melted, it will try to expand and will put compressive stresses on the material surrounding it, which is solid. And this is shown here. So if y-axis is stress and x-axis is strain, as shown here. Initially, the stresses will be compressive, so they are negative. And once the elastic region is exceeded, we'll enter the plastic regime, as shown here. However, once the source or the torch moves away and the material is no longer superheated, so now it will begin to solidify, and this will lead to contraction of the material. What this contraction will do is actually induce tensile stresses in the surrounding material, which is shown by this green unloading curve. As we would know, this unloading occurs parallel to the direction or parallel to the slope of the initial loading curve along the Young's modulus. And once this entire material has solidified, we are ending up with this residual amount of stress which has not been relieved, which is known as your residual stress. Now, if the residual stress is tensile, as shown here, this is a problem because, as we know, no microstructure is perfect. Your material or your build part will often have some small pores or will have some build cracks. And in the presence of tensile residual stresses, these cracks will continue to grow. Whereas if by some process such as in situ hammering or in situ shot peening or laser peening, if we were able to induce residual compressive stresses into our material, into our part, what would have happened is, had a crack formed inside the part, the residual compressive stresses would have, say, tried to close that crack or would have inhibited its further growth. Another common defect which is associated with worm or most AM processes in general is porosity. We never really end up with parts that are 100% dense. Processors and manufacturers will claim some 99.9% density, but that is again highly subjective. Often it is shown just for, say, simple geometries such as a cube or very small parts. Typically, we do end up with porosities, even they might be at the microscopic scale, but they are never, say, fully absent. Porosity in part often leads to components with low mechanical properties and poor fatigue lives. Now, the porosity, in fact, is categorized into two broad categories based on whether they are raw material induced, that is, your feedstock had some contaminant, or the surface of the feedstock was oxidized or in some way damaged, which might have induced porosity in your final build part, or they may be process induced, such as because of unstable process, or maybe your arc shielding was not good enough, or the path planning was poor. Now, these porosities can be controlled by several methods, some of which are listed here. The contact angle that your bead forms with the substrate also plays an important role. So typically, say if this bead forms, if measured from your deposited bead. If this angle is greater than 90 degree, we can expect that upon deposition of the next bead, say somewhere over here, there will be this region which forms a void because material is not able to reach there. Whereas for this other case, when we deposit the subsequent or the adjacent bead, material already exists in this region, thus there is no porosity. Another class of defects are cracks or delamination, also known as hot tearing. So high temperature and material characteristics are the major reason for crack and delamination in warm parts. Cracks can be of several different types. Two are listed here, but there can be others. So solidification crack due to obstruction of solidified grain flow or high strain in the melt pool. Grain boundary crack due to differences between boundary morphology and potential precipitate formation or dissolution. There can also be liquefaction cracking. There can be ductilated dip cracking or even several other mechanisms. Now, delamination between adjacent layers can occur either due to incomplete melting of the pre-built layers or substrate. This defect is visible and cannot be repaired by post-process treatment. And often you would come across some videos where the deposited bead simply bounces off explosively from the substrate because of the delamination effects. To prevent this defect, pre or in situ process treatment such as preheating need to be considered. It can also happen if the say the thermomechanical properties of the substrate and the build material are very different. Say if the coefficient of thermal expansion or the thermal conductivity is very different between the substrate and the material being deposited, then such delamination defects may occur. The susceptibility of various materials to these different classes of defects is also uh, plotted here in a very useful diagram. So say if you're working with titanium or titanium alloy, you're mostly susceptible to oxidation, whereas the chances for delamination are low. Chances of cracking are intermediate, whereas the presence of residual stresses and the propensity for deformation are on the higher side. Now, most of these processes that we discussed typically would require no support mechanisms, or we would only be working with very simple geometries. This is an example of such machine. We are simply depositing on a flat plate with no B or C axis. However, we may also use multi-axis kinematics for building more complex parts, in which case the table is tilted so that the deposited bead is always normal to gravity and no support structures are required. Additionally, we could also work with robotic arms for the deposition of parts. As we already discussed, this also allows us freedom of movement and multiple degrees of freedom. Here is an example of parallel kinematics being used in WOM. You may refer to the video for further information. And this is a prototype of a WOM system with hybrid kinematics. Okay, one slide appears to be missing. I'll just load it. Please give me a minute. The next set of slides for this week dealt with TIG and plasma warp. Now, while there are some fundamental differences between the two processes, often they are used interchangeably, and we'll see why that is. So again, on a subsystem level, we are working with wire material which are metallic. The material flow is again continuous. There is no drop on demand system. The machine kinematics can be serial, parallel, or hybrid based on your design. The energy source still remains an arc. However, this time we are using a non-consumable electrode, which is a tungsten electrode, for generating this arc. This process is very similar to your TIG welding process. So where you have this hollow electrode with a TIG wire, that wire with a tungsten electrode, the wire which will be deposited is actually fed from the side, and the arc is established between this tungsten electrode and the workpiece, and your material is deposited. Typical deposition rates can be between 15 and 30 grams per minute. A typical tungsten inert gas welding setup would consist of a welding torch at the center, of which is the tungsten electrode. This is a non-consumable type of electrode. So in this case, we would want most of the energy to be liberated on the workpiece side, which would imply that typically we would want to work with either an AC power source, or we would want to work with a DCEN or direct current electrode negative setup. The non-consumable electrode creates an arc, which creates a molten pool in the substrate or the pre-built layer. Now the inert gas is supplied to the welding zone through this annular path surrounding the tungsten electrode, or this region shown here. I will just highlight it. This annular region shown here. And also this helps in ionization of the arc. The filler wire is fed towards the molten pool, which after getting melted deposits the material on the substrate or pre-built layer. Unlike MIG-WOM, there is no separate control over the wire feeding process. There is separate control. So here we can control the electric current and wire feed independently. So we have an additional degree of freedom. As we were discussing, because of the non-consumable nature of the electrode, we do not want it to get, say, we do not want it to lose much of the electrode, or we do not want it to degrade over time. Thus, we would want to subject it to as low energy as possible, because even if the temperatures are not high enough to melt the tungsten electrode, repeated or continued exposure over time to such high temperatures may still lead to deterioration in its properties. Thus, typically we would use a DCEN or direct current electrode negative type configuration, or an AC configuration for such cases. Often when a step pulse DC current is used, the current level is maintained at two levels as shown here. So rather than having one high constant current, we can simply have this square or rectangular waveform. The low level is the background current, which is used for cooling the deposited material, and the peak current is used for melting or deposition. Now, plasma cladding is similar to TIG cladding, and this also uses a non-consumable tungsten electrode. However, in TIG cladding, the inert gas is used only for shielding purposes. In plasma welding, however, the shielding gas serves two purposes. First, it is fed into this inner core. So now this region is also cold. It has an annular section, and you have gas flowing into this annulus and coming out from here. This serves the purpose of ionization and establishing the arc. And this argon gas is also fed into this outer annulus, or maybe I should highlight it with a different color. And this gas performs the purpose of, or acts for, shielding. The tungsten electrode here is not really exposed outside. It is still here, however, it comes only till say some intermediate distance, and the arc is established, which leads to ionization of the argon gas, which leads to plasma formation, and this plasma formation continues the arc. Plasma is more popular than TIG for WAM purposes because in this case the tungsten electrode is not projected outside, it is more protected. Thus, the bead height can be increased significantly without any dangers of say say collision or deformation of the TIG electrode. Now, some simple setups are demonstrated here. This is one using a robotic arm. We see the wire being fed by the side, from the side. The plasma torch is here, and the inert atmosphere is maintained. We also see that this layer is still very bright, so it might have just been deposited, and the head would have just lifted from the surface. Now, similar to the case of MIG worm process, even in TIG worm, the control and modulation of various process parameters is important for controlling the build quality and the build properties. In this case, the parameters corresponding to power would be the arc voltage and the currents, such as the starting, main, reduced, and final currents, as we saw. Because typically, rather than having a constant DC voltage, as in the case of MIG, in this case, we would have a modulating voltage, which would say typically be a square or a rectangular wave. The wire material, in terms of the composition, the coating and coring, its diameter and wire feed rate are also important parameters. Again, the gas which you are using, because in this case, the gas also serves the additional purpose of uh, turning into plasma. So its composition, proportion, its flow rate, and the pre-flow and post-flow periods. For deposition, the layer thickness, bead width, bead height. The torch and path are also similar to MIG, typically accounting for, say, the area filling strategy, the step over increment, and machining allowance. The torch would have the standout distance or distance between nozzle and base plate, the distance between electrode contact tip and base plate, which will affect the arc characteristics, and the speed at which the torch is moving. In this case, the geometric modeling is very similar to MIG, and so the single bead, multi-bead in the XY plane, multi-bead in the Z plane expressions remain the same. There are no additional considerations for these cases. However, additional considerations come into the picture when we are talking about the exact position at which the molten droplet of the wire which is being fed from the side will land. Will it land or will it get transferred in the form of these small droplets as shown here? These discrete droplets which may fall on the substrate, which may splatter away, or which may not, say, get deposited uniformly. Will it be this wire plunging type phenomenon where the wire is being fed at a very high velocity such that it does not have enough time to melt, and the other it is colliding with this molten melt pool while still being in solid or semi-solid state? Or will it be this equilibrium type of configuration where the wire is being fed at an optimum speed? It gets molten, but it only gets molten very near to this, uh, say, melt pool. Say if this is the melt pool. And thus we have this bridge, this liquid bridge, which connects the incoming electrode wire with the existing melt pool. And the deposition is occurring almost in a quasi steady state fashion. And another case study is given here. This has been borrowed from this paper by Geng on the optimization of wire feed for gas tungsten arc welding based additive manufacturing. It is important to find out the droplet landing position in TIG worm in order to have more accurate system with better control over the deposition characteristics. And so these are the assumptions for their model. The tip of the wire will be in the weld pool after molten droplet formation, and hence tip of the wire is assumed to be adiabatic. So no heat transfer across this surface right here. The shape of the arc is assumed to be Gaussian, That is not just the energy intensity itself, but the very shape of this arc in space is like a bell curve. The height of the tip of the arc is same as the arc length. The arc column boundary is the position where 95% of the maximum heat flux occurs, and the drop will fall vertically at the same location where the tip of the wire has melted. It will not undergo any further motion, say due to interaction with the arc or the plasma which has been established, or it will not have any remnant of its initial velocity with which the wire was being fed. It will simply, once it has molten, it will simply drop vertically downwards under the action of gravity. And under all of these assumptions, we can have these expressions, say for the equation of motion of the wire as a line. Sorry about that. And we can calculate what is the amount of energy that the wire is taking in as it is traveling through this plasma, and at exactly what time step or at exactly what position has the wire taken up enough energy for a part of it to be molten. We have already performed some similar calculations previously for the case of laser, where the energy distribution across each cross section was also Gaussian. So these expressions might be familiar to you, such as this one, where we looked at the energy which is contained in such a small disk at a radial distance Ri and of a thickness Dri. And then we integrated over the entire region to find the expression for the maximum energy. Finally, we end up with this expression that is required to melt just the tip of a small length dl, and to find out how long it will take for the uh, wire to acquire this energy, and what distance that segment of wire would have traveled inside the uh, plasma during that time. We perform these further calculations and end up with the expressions. So one of the examples has also been solved here. I'll not go into details of it in the interest of time. The landing position has also been calculated. The defects in the case of TIG, maybe this is not MIG, I just made that correction, are similar to MIG based ball. However, the additional consideration of omnidirectionality comes into the picture. The term itself would indicate an equal sensitivity of the process in all directions. And the example of omnidirectional antenna has been given, which will send or receive signals equally well in all directions. Similarly, for a process such as this to be omnidirectional, irrespective of the direction in which we are printing or in which the deposition head is moving, the deposited bead should have similar, or in the ideal case, identical metallurgical and mechanical characteristics. The geometric metallurgical properties of the fused layers are independent of the direction of movement of fusion source in the xy plane. Only then the process would be called omnidirectional. But what was observed here, say, based on a typical configuration when you have the plasma coming in the center and the wire being fed from this side at different positions, say at this original position corresponding to 0 degrees here, position 1. As expected, the wire is being fed from one side, the arc is in the center, and deposition is occurring. Now this black circle traces the path of the torch, whereas the red circle traces the path of the bead. When you move to position 2, or as you're moving in the clockwise direction along this path, now suddenly, because the wire feeding direction has remained the same, now it turns to a case of front feeding, because the arc or the torch was moving along this direction. At each point, it will move along the tangent to the circle. So here, it is moving say parallel to the direction of feeding of the wire or anti-parallel to the direction of wire feed. Thus, it becomes a case of front feeding. When you move further away to a different angular position corresponding to 180 degrees here, now the direction of feeding of the wire has remained the same, whereas now at this point, the torch again continues to move along tangents to this path. Now it is moving orthogonally to the angle of feeding, so this is the case of side feeding again. Whereas for this fourth position, corresponding to this angular position of 270 degrees, the torch continued to move tangential to this circle. Now it is moving parallel to the path of the direction of the wire feeding. So this turns into a case of back feeding. Now it was also calculated how for each of these angular positions the bead characteristics vary. And so the red plot here in this curve gives us the deviation in width from the design value, whereas the plot in black gives us the deviation in height. And as we can see, as the angular position is changing, the width and height of the bead is changing considerably. Thus, the process cannot really be called omnidirectional because based on the direction along which this deposition is happening, the bead characteristics are totally different. A few changes have been proposed, or these technologies have been proposed to overcome this lack of omnidirectionality. One is where your feedstock is fed directly into the fusion source from the center. So you have the coaxial feedstock and coaxial fusion source. Second is where your fusion source is coming from the center or coaxially, and the feedstock is coming from all sides. This is probable for a wire-based feeding process, sorry, powder-based feeding process. But for wire, it is not so practical because from where we will come up with this continuum of wire which is getting fed through an annulus. Next is the feedstock comes out from the center or coaxially, and the fusion source is coming from the in the form of a cone from an annular section. This has been implemented both for laser and maybe also for arc-based processes. And the most common and perhaps the easiest technique is that dynamically adjusting the feedstock feeding direction so that the angle between the direction of motion of the torch and the direction of feeding of the feedstock is maintained constant. So when the direction changed, the feedstock also rotated suitably so that the angle theta between the two was maintained. And here are different examples of each of these types. So when you have coaxial fusion source and surrounded by feedstock, while this might not be a continuous annular feedstock, it is replaced by 3 wires. This can also be 4 wires. And I've also seen systems where these wires can rotate continuously. So it's not like they just deposit in one direction either. This can also help in increasing the deposition rates. Another process which has been patented is the coaxial feedstock and surrounded by the fusion source as shown in this diagram here. And then you have the rotating assembly which also dynamically adjusts the feedback for as per the deposition direction. And here we see a large part which is built out of the stick-based worm process, and this is a titanium tank. So as we discussed, worm is really one of those processes which has industrial scalability and can have some actual commercial prospects in the upcoming times. So now let us just break for a short while and then we'll solve some example problems. So thank you for your patience and let us resume. Now we spoke about thermal cycling in additive processes, and this is a simple study which I had performed for the purpose of demonstration in this course. So here we're just depositing a very simple geometry by um, say laser DED. And what I've done is I have picked this intersection. So you see the macro geometry to the left, and I've just numbered these nodes as per the layer. So I picked one node at the contact of the substrate and the first layer, then N3, N6, and N9. And we built a total of 12 layers, and we'll check uh, what was the thermal history at each of these nodes. And the total build time it appears was some 1500 seconds. So we see these small fluctuations, these small spikes in the temperature. And it will be easier to follow if we come from the top down. So for the final layer that was deposited, or layer 12, we see just this single spike till 1350 degrees Celsius, which was actually the melting point of the material in this case. So in fact, it was 1370. And this single spike, which corresponds to the time when the energy source passed over the 12th node. So we kept on building on top of this. So N12 would have been somewhere here. Now, if we see for layer number 9, uh, or at which the temperature was measured at this node N9, we see these four spikes. Now, this one, as we know, is corresponding to the build in this layer. So if this was 9, 10, 11, and 12, and further we see that this also corresponds to the same time step. So if I were to just project it, it corresponds to the same time step for all of these. Thus, we see that for the already previously deposited layer 9, upon the deposition of further layers, the temperature shoots up. For the next immediate layer, layer 10, it almost reaches melting points, as shown here by this spike. Whereas for subsequent layers, this effect, while smaller, still reaches temperatures of in excess of 450 degrees Celsius, which might be sufficient to induce some phase transformations or other effects. Similarly, this is true for all of the previously deposited layers, as seen here, say for layer 6, layer 3, and layer 0 feels these spikes for the deposition of all of these layers. And on the left here, we also have the variation after deposition of just one layer. So layer 4, this would have occurred because of layer 5. This was for 4. Corresponding to 4, we have a peak here. For 3, and so on. Thus, we see that the effects of thermal cycling are very real and very significant. And often we can explain, say, inhomogeneity or anisotropy of properties on the basis of such effects. Now, let us look at a few questions. So, in which of the following cases would an AC source of electric power be useful in the context of MIG-form? So, just for a quick refresher, if this is our substrate and this is the wire being invisible wire being fed, we can have a variety of configurations. So either we have this positive, this negative, or we have the job negative and the electrode positive, or we connect them via an AC connection. So in which case would the AC source of electric power be preferable? Is it option A for obtaining an intermediate depth of penetration. So as we remember, in the case of DCEN type of setup, 70% of the energy was liberated at the job. For DCEP, 70% of the energy was liberated at electrode. As for the case of AC, an intermediate depth of penetration was found because of the intermediate liberation of energy. So option A is correct. Is it for the deposition of metals which are easily oxidized, such as aluminum and titanium? This is true. And we saw how if we are using an AC voltage supply, the regular reversal of the polarity helps in breaking up these oxide layers and enables the deposition of material. Is it for reducing the overall power consumption? This is not a complete statement in itself, and we do not really have any conclusive evidence to say that by using the AC source of power, the power consumption is reduced. It might just as well go up. So what we can definitively say is both options A and B are correct. The second question, the functions of background current and peak current in pulsed metal transfer are what? So if we remember, we said that for the case of RAM, often a pulsed current is desirable rather than having a uniform current or voltage. And here we have these two levels. The lower level corresponded to the background current, whereas the higher level corresponding to the peak current. So is the background current used to generate droplet of molten metal, whereas the peak current maintains arc? This is incorrect. Do both background current and peak current serve the purpose of generating droplet of molten metal? No. If we could have generated the molten metal at background current itself, we would not have any need to go to peak current. Does the background current maintain arc, whereas the peak current generate the droplet of molten metal? Yes, this is correct. Or are both used simply to maintain the arc? Now, as we remember, the background current simply serves to continue the arc and prevent the extinguishing of the arc, whereas the peak current uh, is corresponding to the time when the molten metal is finally large enough to drop and get transferred to the substrate. So option C is correct. What changes are observed in the case of rotating metal transfer spray or spray metal transfer as compared to non-rotating or simple spray metal transfer? So in one case, you have the material being deposited in the form of these droplets. In the other case, we are giving these droplets further actuation in the form of some spiral path. So as if they're rather than getting deposited in one at one location, they're spread around. So what will happen because of this rotating motion? Does the depth of penetration decrease? This is true because in one case you have superheated metal getting deposited in one place alone. So all the energy is concentrated in one small local region, whereas in the other case, the droplets are spread around. Thus, the energy that they're carrying is also spread around. Does the width of the bead decrease? Because the droplet are being spread around in a larger area, the width of the bead will increase. So option D is correct. And because one is correct, three is also wrong because the depth of the penetration does not increase in the case of rotating spray metal transfer. So we have to look for the option which has these corresponding options correct. So both 1 and 2, both 1 and 4. So option C is correct in this case. That is, for rotating metal spray transfer, the depth of penetration decreases and the width of the bead increases. Question 4. Which of the following statements regarding residual stresses in a warm build part are true? Do the residual stresses Are residual stresses inevitable and cannot be avoided? Yes, this is true. We saw that there will always be some quantum of residual stresses in a built part. It is almost impossible to get rid of them totally. Are tensile residual stresses preferable because they inhibit crack growth? No. As we discussed, tensile residual stresses will in fact try to open up any existing cracks or pores and will lead to further damage. Are compressive residual stresses preferable because they inhibit crack growth? This is true. In an action simply opposite to tensile residual stresses, these compressive stresses will inhibit crack growth. Are compressive residual stresses more dangerous than tensile residual stresses? No. Tensile in fact are more dangerous. Here we have options 1 and 3 correct. So C is the correct option overall. What is the disadvantage of using a robotic manipulator as compared to a multi-axis table for manufacturing supportless structure? Now, as we have been discussing, both may be used to deposit free-form structures. But what changes is that in the case of a robotic arm, so say I'm trying to build some structure, maybe like this. So what may happen is if I were to slice it, I'm trying to build this with a robotic arm. So initially I might be able to deposit the layers pretty easily. But when I reach this, say this flange section here, it is possible that the robot has to go under and then it deposits the part here. So this will correspond to something like an overhead welding. Whereas in the case of multi-axis degree of freedom table, the table would have rotated and oriented itself suitably such that the part, the overhanging region is now lying normally to gravity and there is no need for any support structures. So while both allow us to form these free-form structures, there are certain fundamental differences or advantages. Is it less degrees of freedom? No, both may offer the same number of degrees of freedom. The process parameters may be different for non-overhanging and overhanging parts in the same build. In the case of robotic manipulators, because as we saw, one of the cases may correspond to the case of overhead welding, whereas in the case of multi-axis DOF table, the parameters may remain the same. Is it the difficulty in maintaining inert environment? This is not true. The challenges in maintaining an inert environment may be the similar for both cases. And is it a smaller build volume for robotic manipulators? On the contrary, robotic manipulators may end up having larger build envelopes than your typical multi-axis tables. So option B is correct. Why are hardness values for the first few layers of a component deposited by MIG-worm nearly constant? Now we discussed this in great detail. Is it because the first few layers undergo thermal cycling, leading to a coarser microstructure and low hardness? This is consistent. We know that typically a coarse microstructure with larger grains will have lower hardness. Is it because the first few layers undergo thermal cycling, leading to fine microstructure and low hardness? So thermal cycling will typically lead to coarser microstructure. Is it because the first few layers undergo thermal cycling, leading to coarse microstructure and high hardness? While the coarse microstructure part is correct, this will often lead to lower hardness and not high. And the first few layers undergo thermal cycling, leading to fine microstructure and high hardness. The thermal cycling will lead to coarser microstructures. So option A is correct. Why should we use non-organic piping in the context of MIG-worm? Is it for lower cost? Now we cannot really comment on the cost perspective because we have no definitive reason to think that non-organic piping will be more cost effective than organic piping. So this is highly doubtful. Is it because of less reactivity with common build materials deposited by worm? Now again, it is difficult to comment whether any non-organic piping will be, say, lesser reactive or will have lower footprint on the overall deposition process than an organic piping. Is it to prevent process-induced porosity in the deposited part? This is true, and as Professor Kapil explained, because of the use of organic piping material, some organic compounds uh, also get trapped and deposited with the build part, and because of the higher temperatures, they may liberate some gases. Now, in the molten state, the solubility of gases in molten metals is high. However, when they solidify, this solubility tends to go down and the gases are liberated. The liberation of these gases will lead to pores in the final built part. Is it because non-organic piping produces gases which, when subjected to high temperature, assist in the warm process? Again, this is not true. So, option C is correct. Okay, the next couple of questions are actually about electron beam wire arc additive manufacturing, which we have not discussed yet. So we will stop here. Thank you for tuning in. This was week 8 of the live sessions for the fundamentals of additive manufacturing technologies. I'm Sourav Goswami from IIT Bombay. Thank you very much.
Thank you, sir.